So my topic will improvement of the biomechanical properties of decellularized bovine pericardium towards development of the heart valve. So my table of content will be introduction, heart valve, heart disorders, treatment option, hypothesis, objectives, and objectives are three basically: design and fabrication of bihybrid. I'll go one by one, and then conclusion I'll come to that. So there are two major types of heart valves are there. I think everybody knows in the audience. I don't have to speak on too much on those things, but let me see that there are something here is that here in these things, there every heart valve contains the three layers. Basically, it's a collagen, elastin, and gag, and then collagen, elastin again. So it's a sandwich kind of things. So develop any tissues, we need to stack all those things one by one. Then only we can do that. In this source, heart valve ensure unidirectional flow. That is the quality of the tissue that it has to go only unidirectional. Maintain cardiac dynamics. Has three-layer architecture, as I told you. Fibrosa, mainly towards collagen, towards outflow. Spongiola, mainly toward the gag. Ventricular, mainly elastin, below the inflow. And valvular, endothelial, and interstitial cells also among that one. So the valve disorder, so valve stenosis, valve fail to open fully, and flaps become rigid, thicken, or fuse together. And valve regurgitation is the valve do not close properly, and backflow comes out of that. There are the treatments, however, I think everybody knows, medication and surgery, two of the options. And surgery contains the balloon, valvuloplasty, and valve repair and valve replacement. These three things options are available. And so heart valve has two things, is the mechanical properties and the biological properties. So motivation comes in by understanding the both properties first. Good mechanical strength, durability. This is mechanical valves I'm talking about. And suitable for replacement of the young patients, need lifelong anticoagulation. But in the morning I said people don't use also anticoagulation. So that's one thing which I learned now in this meeting. And biological properties, heart valves said the poor mechanical strength. That's the best things. Fatigue, regurgitation, leaflet tears, and calcium deposition is one of the things which everybody talks about that. And leaflet tears occasionally happens basically. Calcium deposition and pernicious overgrowth. Not suitable for young patients and high cost. So we thought that we can have a tissue engineering approach. This is our approach. So what we did, basically we need a three layers things. So we get native extracellular matrix, which is ECM based decellularized tissue with cross-linking agents. So cross-linking is very important because it gives stability of the tissues. We can use cross-linking agents on synthetic and natural polymers. We can imbibe in that one, impregnate basically, and hybrid scaffold with and without cells. Both we can make it. We have used the mesenchymal stem cell for cells. So what we need basically decellularized tissue with conventional cross-linking agent, but with polymer surface coating and also impregnation. So this is a problem statement, and the hypothesis that deposition of the synthetic polymer into decellularized bovine carp, we have used basically bovine pericardium. Tissue will provide a 3D matrix with adequate mechanical properties required for fabrication of the heart valve. So now onwards, I am going to do basically the biochemistry and mechanical engineering part. So there's nothing in that one. So our three objectives are there. One, design and fabrication of the bihybrid scaffold using decellularized bovine pericardium and a slow degradation polymer suitable for heart valve tissue engineering. So whatever we are putting on top of the bovine pericardium has to be degraded slowly so it can maintain the native things. Detailed biochemical evaluation, I'll talk about that more, and assessment of the silver infiltration into the tissues. So fabrication, this is objective one. So these are the few things are there. The first thing is the decellularization is very important things. Confirmation of decellularization, characterization of ECM, extracellular matrix, selection of polymer and characterization of nanofiber, and fabrication and characterization by bihybrid scaffold, mechanical properties and biological characterization. So decellularization, three ways we can do it. We can do physical or do chemicals, enzymatic, and combination of all. This causes disruption of ECM, removal of the glycosamine. Glycosamine glycans is very important in growth factors. because we don't want to reduce the immune response of the person, because these are the one who develop the immune response when you are there in the bodies. We are using a deoxycholate for decellularization process, and decellularization means there is no cell, only the matrix left. That's a very important thing. So we have to characterize. Confirmation of characterization, we do histology, DNA estimation, histology, GAG. It's all biochemistry basically. So you can see A and B. A is basically where a lot of blue colors are there, blue dots are there. These are nuclei basically. When you do the decellularization, there is no nuclei present. So that's one issue, that there is no cell attachment that after decellularization. We do lot of characterization. Gel electrophoresis also shows decellularized bovine pericardium doesn't have any DNA, whereas the bovine pericardium has a lot of DNA in this lane basically. And we also characterize this DNA in this one also. These are all way to characterize. ECM characterization, because there are 3 layers are there, different tissues are there. So we do trichome, Elsian blue, and BVG staining. After staining, we do some test to prove that this is correct. So we do DMF assays, we do colorimetry, bovine cardium, and you can see them that both have the quality, but there is a reduced quality and strengthening is there in both cases. So our cellularization works in this one. And then we select the polymer, what we want to do. So we have selected clinical trial studies, PCL and PLA. These are known, and chitosan. These are very slow degrading synthetic polymer. There's a natural hydrophilic polymers are there, which can be soluble in water also. Selection of the fabrication techniques, basically we can dip coating also, we can make a solution and dip into the tissue in that one. Second thing, electrospinning. Electrospinning is a really better one, because we can coat the any tissues, any polymer into the surface of the membrane uniformly. So this is a machine is there which can coat them under the electric current. So optimization parameter, fabrication and characterization of the biohybrid scaffold. This collection by the electron microscopy, FTIR, and mechanical strength in that one. So you can see this is the first experiment when we try to align the fibers and see which combination of the fighter, which is PCL and chitosan. So finally, after so many ways doing all this combination, we found out 10% PCL, polycarbolactone, and 1% chitosan is a mixture which is giving the good fiber on the top of the bovine cardium in this one. And this is surface characterization of the biohybrid scaffold. This is A and B, basically you can see them. These are the bovine pericardium, and this is the decellularized bovine pericardium where the cellulars are there, and this is basically high resolution C and D biohybrids are the images are there, which clearly shows there is a groups are there, the matrix is stained, and if they are connected on of the tissue, we have to do FTIR in this one. So this is the hydrophilicity we check with the contact angle basically measurement, and you can see the fresh bovine pericardium and the biohybrid more or less the same one active. And this is the angle test we do with the measurement in this one. We also do FTIR in this when we see whether the bonding attach or not, because attachment is very much, because it should not, with the blood flow, it should not go out of the, when there is a flow of the blood, it should not go out of the thing. And then we also see the mechanical strength also in this one. You can see here the mechanical strength of this biohybrid and the control is more or less same or higher than this one in this case also. So you can see this is all properties. What we have done is, so it stabilizer and give more mechanical strength to those pericardium when we attach the polymer into those things. And this then biocompatibility also, this see that they should do that. So here is very direct contact, assay is there, and then text on extract of scaffold on the cells. What we take this tissue and see whether this is mixing with the cellular X-ray, it is not destroying the other things. Then cell adhesion also we check, the cells are giving adhesion through ECM. This is electron microscopy and fluorescence imaging, and also DNA quantification. These are technique we and gate quantification we do that. So here is basically all this characterization is there, basically done. You can see that what is a hybrid, biohybrid does very nicely. They are attached to the cell membrane, and the fluorescent microscope shows that, ensure that there is a adhesion is there in this one. So MTTSA basically shows there is a no cell, degradation of the cells happen in those cases in this program. And these are different ways that we have done the different cells, stem cell also we can do other things, and we see that there is very compatible on those things. Compatibility means the cells grow on top of that scaffold basically. That's compatibility. So overview, if you see them, we have taken this clue from the native cells, and we have put a cells on top of that polymer ECM cell. We make it, and after making them, what we do, we take a pericardium, decellularize them, and then we can, with electrospinning, we put on the polymer and then grow the cell on top of that, and then see that native heart valve and made heart valve is characterized the same thickness and biological activity and also mechanical strength. In those three we have checked basically. So this eliminating the cross-linking agent that are known to be cause calcification is not there. Polymer impregation and pericardium without processing. That we have done. So we have developed a scaffold which is better than the other one in this one. Sorry. So conclusion of objective one was that optimize cellularized bovine pericardium with 1% DCA. We found the retention of the ECM, means the architect of the extracellular matrix is retained after the decellularization. Synthesized nanofibers, which are impregnated into the top of the pericardium, is also has a solvent system. Optimized fabrication, mimicked tri-layered heart wall structure, that is also equivalent. And uniaxial and properties, I'll talk about more about the reason. Promising the wall and biological analysis, so biocompatibility and hemocompatibility are there. So involvement of the evaluation of the biohybrid scaffold for tissue engineering. So we'll do the fabrication and then uniaxial mechanical strength characterization, and we have the isolation of human wall intestinal cells basically. So VIC cells, we isolate them and put on top of them and see how they are behaving there, and the biaxial testing. So basically it's a mechanical part. And if you see correctly, this is a collagen fiber orientation happens in the this pericardium and versus the heart wall is so different. This is the, so if you align any tissues on top of those things, you need to see this orientation have the maximum functioning also. So first you have to understand the architect and then go for functionality in this one. So the biaxial fabrication was there in this one. Mechanical strength of bovine pericardium is different in axial and circumferential direction. So that's a clue we have it. Alignment of the polymeric nanofiber increases the uniaxial mechanical strength along with the nanofiber, and anisotropy is required for the heart wall fabrication. So you can see here that this is the same images of these things. Decellularized. This is the PCL only. This is the hybrid scaffold, PCM and chitosan, and this is aligned fibers. Aligned means you can see the fibers are almost in unidirectional in this one. You don't find 100% unidirectional, but I'll show you. You have to do the laser ablation for that, and then you can get those kind of things in this regard. So unisexual testing, we have done it, and you can see here that after tensile strength formation, the native versus this one, increase strength basically. Unidirectional, I'm talking about, not bidirectional yet in this one. And you can see time of electrospinning, how much we do that. As soon, if you increase the electrospin fiber coating timing, the number of the fiber whose strength and one by one on top of each other is increased. The strength is increased in one as you increase, but you can't increase too much because the fiber has to be stick to the ECM. That is very important also. So you can't have a too much layer, too much less layer also in that. So the pore size is also important when you do that, because the cell has to go inside the cell. You can't have a stack of the polymer so that it will block the entry of the cells. That is also very important. So we need to take care of that, and these are experiment also. And we have also the degradation, that how much time it takes that polymer to degrade so it can be take the natural shape. So you can see within 30 days, most of the things are degraded in this one. So this is a very important step that we have to do it in this regarding this. This is a basically experimental setup. I think this, we don't have this instrument. So mechanical engineering in the IT department, they help me in doing those things. And this is the one thing which I learned a lot, that if you make any tissue, how do you know how do you measure the strength of that thing? That's very important. How much weight you can put it so that it cannot break, but it can take it. As the heart valve takes the flow of the blood, so there is a strength and pressure is there. That pressure we have to do it. So that's the main thing is there. So there's a alignment is that these are all the cameras basically, and I'll show you next slide that this is the sample. Sample size is this much. This is the base, but where the sample is very small in that one. And then what happened basically, you can't measure it. You have to put a spot on those things and see microscopes, how much movement happened. So everything done under the microscope in a nanometer range, which is pressed, can be measured in that one. So we'll do this direction, and upward direction. So that is a very important thing we do. It took us basically 1 year to do this experiment because we were new, we didn't know how to do that. And they do a very hard stuff, mechanical engineering. Suppose this, they make a fabricate anything metal, they do in that one. So there is a big object is there, they can do better. But this much objective, when they started doing things, then they have to redesign the whole thing and try to do it. So this is the basically, you can see this, this is the pressure they put on top of that and measure it, how much weight they are going to put on that particular tissue and see that one. So the load cell is there in that one. And these are protocols are there, how much we are doing that. So there are 3 protocols are there. I'm not going to show you. And this is the basically final thing comes in this one. And when this comes, the results are amazing. This is the result, unisexual properties, that you do unidirectional pressure, how much change happened basically. So you can see here, this is the axials here in this one, how much we are putting those things and what happened to the tissue, how much weight they can. So you can see the stress is produced in megapascal and you stretch is how much. This is in millimeter. So if you put this much Pascal, 0.1, 0.5, I think 20 megapascal everybody, but 0.1, 0.05 megapascal is very difficult to measure. And that's what we did it. And then there is how much stress they can mean. So you can see 1.5 nanometer, the stress happen on those things. So this is a very important to understand how tissue behave in a system. We do a lot of work, I think, robotic surgery and everything, but the weight and pressure they take the tissue and has to respond, not to get degraded, something like that. So that's a wonderful thing to study in that one. And here is that. This paper, we try to publish it, but we got at least 6-time revision in this one. They were not happy that you are doing a pressure experiment only 1, 2, 3 times. They at least they say 1,000 times to do experiment, then only we'll know. Because what happened in the valve, how many times it goes and closes. So need to mimic the similar kind of things. So we really say that below 1,000 experiment will not accept the paper. So we did 1 year, I think I took this one, and you can see that the normal stress were this real axial and the biaxial, how much difference is there? Very close, nearby. And you can see these are all experimental details and how to plot it in this one and prove your point that yes, they can sustain it. And so many ways we did it. See, you can see here, so many things ways try to do that and convince the reviewer that our experiment is working. And they also helped me actually. They suggested how to do the experiment also, because they also were learning from us, those reviewer in that process. So finally, you can see the slope, what is coming. Now you can see here what I showed in the beginning, that how these stress collided each other. Similar kind of graph, you can measure it in those biohybrid things in this one. So stretch ratio versus stress. That's way. This is the basically variation of the stretch. So you can see the variation. The biohybrid takes linear these things compared to the native pericardium. And here in this one, along to this is a axial direction and this is a circumstantial direction. Both directions they are able to equilibrate, means there is not much difference in the native pericardium and the hybrid cone. That's the main thing. degradation also. And this is all, these are basically testing of different antibodies that yes, our biohybrid contain all those material which has the, in this one, heart valve in this one. So we have corrected a lot of things in this one. This is a biological evaluation of bihybrid scaffold. These are all basically all collagen, collagen 1, collagen 2, memantine, fibrin, and lignin, all present there. So in decellularized bovine pericardium and bihybrid also, which contain the cells, you can see here also in this one. They're much better bihybrid one compared to the decellularized bovine pericardium in this one. And this is also same scaffold, different ways of doing those things. You can see a stain of the different antibodies along with the, to characterize what is present in the cells. And you can see the quantification of total GAG, total DNA quantification. So very less DNA contained here in this one. DNA contained in this one, contained to bihybrid. So more or less, this shows that our bihybrid is much better compared to the normal bovine pericardium. So the conclusion is we have fabricated aligned biohybrid scaffold, uniaxial mechanical properties shows the enhanced properties along the axial direction. Biaxial analysis also showed anisotropic property of the bihybrid scaffold, a 20 times more the strength of the stiffness of the axial direction. Isolation of the VIC and other adhesion and proliferation of the bihybrid scaffold, and potential material for autologous valve tissue engineering. That's we predicted in this one. Third thing was that alignment. How do you align these cells into the direction? Because it's very important. I showed you with the very first slide that pericardium, the pericardium versus this heart valve, both are different alignment of the cells. So we have to see that one also. So we do the laser micro patterning of the bioscaffold and study patterning of the biocompatibility and study of the patterning of the mechanical properties. These three experiments we did it. So here you can see here in this side that this is not laser ablated. This is a nanosecond laser ablated. You can see how aligned fibers can be created on those things, but exposing to the nanosecond of the laser in this one. So same image of the decellularized pericardium here, same image of the bihybrid scaffold after ablation, 60.64 microjoules, which are very, very minimal, and energy is very little in those ones. So they don't destroy the cell, but they just align those things in this one. And then effect of the laser, you can see energy compared to the DBA micro, they're always increasing the patterning in this one. And that also shows the bihybrid patterning was different. So it's in this case, joules energy point of view. We also characterize with the FTIR that there is no bonding is lost in those things basically. So here is this one. This is FTRI. This is a DSC basically. So it's close to the what is the native versus the bihybrid, and also scaffold shows that young modulus. Young modulus is basically tells about the properties and strength of those things which are comparable in those after laser treatment. That's not destroying the property of the tissues basically. So you can see here very nice alignment scaffold here in this one, and this basically groups are very important because cell infiltration has to be there. Because of cell infiltration, we require those kind of things. So image showing the adhesion of these are MSC molecule which are mesenchymal stem cell as taking it there in this one. Before and after the laser ablation, you can see here nicely this one. This is the biological characterization of those things. So we can see here that is stained with the fiber. They are all left. There is nothing. So you can see very nice cell adhesion on top of those groups, basically on top of that. And the groups are still visible in this case. And this is the basically correct another way of showing potential, showing them. This is biohybrid and decellularized. They have a similar property, but better bihybrid has them in this one. So the conclusion is that nanosecond pulse laser can be used to selectively ablate the portion of the polymer layer on the hybrid scaffold with preserving their overall structural integrity, which is very important. Optimization of the fluence in step and the mark time added to the microchannel with optimal width of the depth. The depth of the microchannel is very important. And fibroblast and the stem cells show the better adhesion in both cases. So here is our final thing is there. We take the bihybrid scaffold, we do the nanosecond ablation, and you see the micro patterning start in this one. and then cells are attached on those things, characterize them, and now this scaffold, and this is ready for making these valves in this one. So this is our conclusion, which I showed is the last objective is very fabricated microchannel biohybrid scaffold using nanosecond laser ablation achieved enhanced cellular colonization in the biohybrid scaffold, which is required for the tissues basically. Further, we would like to test these things because nowadays there is, I was talking to somebody told me that there is a artificial intelligence is there these days, which can give you the total size of this valve, how much required. So if you can get the from patient, we can cut this valve into particular size and replace with them is a better option. So this is the one which we need you guys to help us in doing those things. These are some of the publication I can share with you. Janvi was the first, that was the lady I was talking about, Sarpali Janvi, and this we have 3 papers out of these 3 work basically. Every chapter has given you 1 paper. Thank you all.